Welcome class to our third related rates problem solving video. This video is related to the classic problem involving a conical tank. And so you see a picture of a conical tank here, and I want you to notice a couple things going on. One is you have the actual tank itself, which is the large cone, and you have its radius of 5 and its height of 14, which remain constant because that's just the tank. But then you have this similar cone here in blue, which is the amount of liquid that's in this tank. Usually water is the liquid we use, so I'll just refer to this as water. So the water in the tank actually forms a similar cone inside the larger cone of the tank. And so when we use the volume formula I'm talking about the radius of the surface of the water in the tank, and I'm talking about the water level. So the height is not referring to the height of the tank, it's referring to the height of the water, the level of the water inside the tank. So keep that in mind as we attempt this problem. So here's the problem is we have water flowing from the conical tank, so understand it's draining at the rate of 9 feet cubed per minute. The tank stands point down like we saw in the picture, point down, and has a base radius of 5 and a height of 14, which also we saw in the picture. The question we're being asked is how fast is that water level falling when the water itself is 10 feet deep? So the first thing we want to do is identify what we want. We need to figure out what it is that we're being asked to find. If you recall, the end of the problem said, how fast is the water level falling when the water itself is 10 feet deep? So, okay, we need to consider this picture here. The water level would basically be this value of h. That's the height of this similar cone formed by the water in the tank is also the water level, the level of water in the tank. And we're trying to figure out how that's changing because that water level is going to decrease as the water drains out. So we're trying to figure out the change in height, really, the change in height of this water cone, if you will, with respect to time. At the very instant, so notice here, it's not like overall, it wants to know how fast is the water falling at the instant when the water is 10 feet deep. So that would be at the moment that this height is 10 of this cone is also how deep the water is. It's also the depth of the water. So basically what we want to find is dHdt. So that's the change in this height with respect to time when this exact height is 10. Second thing we want to do is to determine what we know. So we know that the water is flowing from a conical tank at the rate of 9 feet cubed per minute. That is huge that it's feet cubed, because what that tells me is that's the volume. That's the change in volume with respect to time, feet cubed per minute. So I know that the change in volume with respect to time is -9. Negative because the water is actually draining out, so the volume is decreasing. Now, the tank stands point down and has a base radius of 5 feet. So that tells me, of course, that my radius is 5. And it also tells me that the height of the cone is 14, so I know that. And what I'm trying to figure out is how fast the water level is falling when the water is 10 feet deep. Okay, now I need to somehow be able to relate radius and height together. And I can see here that the ratio of radius to height of the smaller cone will be proportional to the ratio of radius to height of the larger cone because they're similar cones. So even though these values of R and H will be changing as the water drains, their ratio will remain proportional to the ratio of 5 to 14. So that's a huge piece of information. So the ratio of radius to height in each of the similar cones that I would get as the water drains will remain proportional to the ratio of 5 to 14. So now it's time to connect what we know to what we want. first thing we'll begin with, which is usually how we do these related rate problems, is we start with a formula. So we're going to use the formula for volume of a cone. Now remember, this volume is referring to the volume of the water in the cone. It's not referring to the cone itself. This R is not referring to the 5 up here. It's referring to the radius of the surface of the water. And this H is referring to the level of the water. Okay, now I know the change in volume, and I want to find the change in height. So if I could somehow figure out a way to get rid of this R and just get V in terms of H, what I know in terms of what I want, I will be in a very good position. So that's where this proportional ratio comes in. The ratio of this smaller radius of the water cone to the smaller height of the water cone is equal to or proportional to the radius of the tank itself to the height of the tank itself, so 5 to 14. So multiplying both sides by H, I can cancel out the H's and just get R by itself. So I can see that R is the same thing as or equivalent to 5 over 14H. So I can plug that in to the volume formula here for R. I can substitute that for R. And so that would get me this expression here, simplifying that. So the 5 squared becomes 25 in the numerator. The 14 squared becomes 196. Multiply that by 3 and you get 588 in the denominator. And then the H squared times H gives you H to the third. So that right there is the jackpot. We have hit the jackpot because I have related what I know directly with what I want. So all that's left for me to do now is to differentiate both sides of that equation with respect to time. So here's my equation here. I want to take the change of both sides with respect to time of this equation. So this is an implicit differentiation because I'm not taking the derivative of v with respect to h, I'm taking the derivative of v with respect to time, and then also the derivative of h with respect to time. And so that's what's happening here. So the derivative of v with respect to time, that's just dv dt. So that's the left side. Now, to take the derivative of the right side, I have to use the power rule, the constant multiple rule, and the chain rule. The constant multiple rule just says take this constant, 25 pi over 588, and multiply it to the derivative of h to the third. The derivative of h to the third would be 3h squared. So I just multiply the 3 to the 25 over 588, and then the 3 reduces with the 588 to come back to 196. So the 3 times 25 over 588 becomes 25 over 196. The pi just stays there, and then you have to subtract 1 from the power, so the 3 becomes a 2. But then the chain rule says I have to multiply this by the derivative of the block, the derivative of the function that was being raised to the third power. So the derivative of h with respect to time is just dh dt. Okay, now we are almost done because I know the change in volume with respect to time was -9, and it asked me to find dh dt at the instant that the water was 10 feet deep, which was the height of that water cone, so I know that that is 10. And then I have enough information now to solve for what I want, which is dh dt. So what I did is I just combined the 25 and the 10 squared, it became 2500, and I went ahead and put pi in the numerator because what I'm about to do next, it helps to make sure you know what's in the numerator as opposed to what's in the denominator, because I want to isolate the dh dt. So I want to get rid of this number that's being multiplied to it. The only way to be able to do that is to multiply by its reciprocal. So I'll multiply both sides of this equation by 196 over 2500 pi. So that on the right side, all these will cancel and I'll just be left with dh dt. And then on the left side, it just turns into a number, -9 times 196 divided by 2500 pi, and that turns out to be approximately -0.225. So we have our answer. Now we just want to go back and make sure we answer the question being asked. The question being asked was, water is flowing from a conical tank at the rate of 9 feet cubed per minute. The tank stands point down, has a base radius 5 and a height of 14. How fast is the water level falling when the water is 10 feet deep? So the answer is the water level is falling. So notice I don't answer with a negative number, I just answer with the word falling. And that implies negative or decreasing. So the water level is falling at a rate of 0.225 feet per minute, because we want to use the dimensions for height, and which is going to be feet since the volume is feet cubed per minute. Or if I want to understand what that looks like better, I can change that into inches. Just multiply this number by 12 since there's 12 inches for every foot. So it's 2.7 inches per minute. And that's our answer to this question. Stay tuned for our fourth and final video on related rates problems. I'll see you there.